Okay, we'll give it 30 seconds, 20 seconds maybe. Still got a couple of people walking in. Okay, we'll get kicked off. There's still people milling around outside. Good morning. A quick show of hands. Who's into banking? Well, I'm sure everyone's got a bank. Who actually works at one? That's most of... No, that's about half of you. What else? What else are you in? Telcos? No? Any other subjects? Any other businesses? E-commerce. Yeah, good one, I suppose. Retail? Okay, so what I'm going to talk about today, I'm going to try and get through these slides quite quickly. We've got 50 minutes, and I actually want to go into some code afterwards, so I want to show you a working example of this, and it's something which I really get a chance to do. Obviously, if I was to go through the actual examples of this, it's going to be pretty complicated, as you'd imagine. Anybody showing you through some large amount of enterprise code is going to take some time to go through it. So what I've tried to do is sort of show you pictorially what the flow is of these sort of typical applications, and then I've knocked up a quick example which literally fits on a couple of pages, so you can actually see the stuff going through, and then we're going to run some queries. So that's my goal, to get through this as quick as possible. So you obviously get the slides afterwards, so if I speak or go through them too fast, then apologies for those. You can revise afterwards. So how hard can it be in the banking? So obviously I'm going to stand here and tell you that it is unbelievably hard work. And that's obviously what I'm going to go through and try and convince you that it is pretty complicated. But the complications aren't always where you expect them to be. Sometimes the technical things are the easy part, and then a lot of hard work in the politics and the tuning and various bits. So I'm going to look at some of the external influences at the moment. My goal is not to go through those in great amount of detail. There's 2 slides on that, just to talk about some of them. Dodd-Frank, for example. Look for the need for some of these changes, why these changes have been driven. Look at some of the complexity of these, and just when you think, okay, there's one message type turning into another, I'm going to show you the different types of applications we got in the banks, and just why this becomes quite a major problem, where we need literally thousands of people to run these things. We're going to look at a bit of SQL, NoSQL, and then the drive towards in-memory databases in this sort of case. And again, that's the sort of example that I'd like to show you as well afterwards. As I say, hopefully a code demo walkthrough. So, as I said, 2 slides. This is the business part. I won't go into this in a great amount of detail, but I'm sure everyone here remembers not that long ago, and we're still on the brink of some interesting things happening at the moment in Cyprus, but it happened here about 5 years ago in 2008 when the banks pretty much collapsed. People did runs on the banks, and the stock markets went down. And 2 people, Mr. Dodd and Mr. Frank, got together and proposed to Congress in the US that something should be done about it. It was proposed, it was signed off by Obama, and the same thing happened in Europe as well. This went into effect, and it's absolutely huge in terms of both the impact and the size of reading through this, and the impact of what this encroaches on. But some of this is that the banks actually have to report what they're doing. So rather than come up with these fictitious trades, or trades that somebody's hidden somewhere, that they create some account, and they say, oh, there's this really exciting thing that's happening off in California, and we've got to invest lots and lots of money into it, and all of a sudden it turns out to be fairly fictitious, or has not quite got the same rating that they thought it had, and it collapses, and therefore all the derivatives and trades behind that go with it as well. What you now have to do is to register every part of the risk of these trades. So if you're buying one thing against selling something else, you've got to find out what the things are that you're buying, where they come from, and where the parents of these companies or banks come from. In the old days, when you bought, let's say, a commodity from a stock market, you had the risk of the broker that was selling it to you, the risk of the country that the broker was in, the parent of the broker, the bank that was selling it to you, the parent of the bank, the country where the bank was, and all these added little bits of risk, and this has somehow got lost along the line. So what they're trying to do is put this back into it. So ultimately, what this means is this, the Dodd-Frank and some of these other things that are driving towards changes. We're trying to get out of the nasty old formats from 20, 30 years ago into XML. Obviously, that's not very easy when you've got every single bank on the planet using these things. You've got to slowly drive these changes through. And what the banks now have to do is every time they file these, create these derivative trades, swaps, they have to register them with a registering body. Effectively, the DTTC is one of these, where everything has to be registered so that it can be checked up on, so that the governments can see what the exposures are with the banks. This is sort of quite interesting, because if you look at the average sort of messy architecture of a bank, these are things that, for those of you who have worked in banks, you'll see frequently on a wall. This is one I actually stole off a wall, or stole from the source of the thing that printed it on the wall. I've yet to find anyone that's recognized it, because these things change every sort of couple of weeks, and they go in different colors depending on what someone's trying to demonstrate. But all of these different parts, if you imagine, and I'm going to go through this, when the trade is executed from the instructions come from the middle office, goes up to the front office where the people execute these on the stock exchanges. It goes back down into the middle office, gets cleared, and goes onto the settlements in the back office. All these different parts of the bank have different parts of the trade life cycle. So a single trade could last, it's not instant. For each small part of the trade, it may be instantaneous or relatively quick. We're talking sort of milliseconds in the front office, but the duration of that trade as it goes through can last for years, because you could be buying something today or buying something in 6 months' time, which matures in maybe 10 years' time, for example. So we've got a lot of data everywhere. One of the huge problems we have with the banks is that they typically buy very large amounts of equipment. You won't see them using, for example, Amazon, because most of them have 5, 10, 15, 20, 50,000 machines of their own anyway. And of course, with all of this, they buy all of the databases. They typically spend 9 figures, so we're talking 100 million plus, give or take a little bit. So we're looking at deals in the region of $100 to $200 million with something like IBM, with Oracle. A bank here in London recently did a survey of how many databases they have. They had 39,000 databases in the bank. There's different databases around, of which 20-something thousand of those were Oracle, and the rest, you can imagine, were mixtures of DB2 and Sybase, and that didn't include Access, by the way. They estimate that there's another few tens of thousands of Access. Problem is now, some CTO has chosen this, been to the golf course, gone out with the guys from IBM or Oracle, bought $100 million worth of IBM kit over a 5-year contract, and there's no way you're going to get any other product in there, because you're competing with this $100 million worth of, I'll interchange currencies, it doesn't really matter, dollars, pounds, etc., of this kit. And that's why anybody selling NoSQL solutions or in-memory solutions is going to find a really hard job to get in against this, because IBM is going to come up with their solution, Oracle is going to come up with their solution, which compete with the other solutions that are trying to get in. So these are the challenges. This is roughly a sort of functional landscape. What I've tried to put on here, so if we look from the top downwards, we've got the front office at the top, middle office obviously in the middle, and the back office at the bottom. You probably can't read some of those bits. Let me just read out a few. So we've got priority position keeping, queue management, prime brokerage support, risk control, payments, funding, asset services, etc. So all these things, again, if you work in banking, you'll recognize these. Each one of these are applications. Inside these applications, most of them probably written in J2EE or some Java, enterprise Java, most of them with an entire team behind them, with a project manager, etc. Some of these may have been running for several years, therefore there's nobody actually running. There's just somebody who turns it on and off or reboots it every now and then. So this gives you some idea. Now if we follow a typical trade, so we just go through little parts of this, we follow a typical trade, starting now to look at the integration of these. So as I say, the middle office suddenly decide the new strategy is let's get out of Asian Pacific trades and let's go and buy energy in the US. So they leave the instructions for the front office guys. Guys, sell everything you've got in Japan and buy US energy, because that's maybe the strategy they want. So these guys go off, they try and sell it. Each time they sell it, when you try and sell 1 million units of something, it doesn't necessarily go in 1 million units, it'll go in little bits and pieces. These are called blocks and allocations. So we get one order with many fills in it. So we've got one-to-many relationships on the top. So we're looking at fix. There's no time for brackets in here, so we're low latency. These are very efficient protocols that we typically get in the front office. As we go further down, we start to see comma delimited files. This is because they're going typically into and out of databases. This is where we see some of our many thousands of databases. Further on down, we get into internal proprietary XML. So this is XML where somebody's trying to refactor something, or we may be moving towards the bank's internal canonical format in XML. Then eventually, as we get down, we get into more sort of standard XML formats for external usage. So that's just one department or one line of business within the bank. Then, of course, you get typically 4 or 5 of these across each bank internally, and then you go outside, and then you've got that across each region. So that somewhat complicates things. And then with each part of that, adds then all of the further communication with all of the external formats. And looking at that, we've got things like Swift, ISO 20022, FPML, market serve, DTTC, XBRL, all of these sorts of different reporting standards. So you can start to see some of the integration issues that we have with this. One of the standards that's used for defining swaps, in fact, the main standard at the moment for defining swaps is FPML. It's the Financial Products Markup Language. This is where we start to get into the technology. So this part, here's my laser. This part here is a super zoomed out version or picture of the FPML, obviously nicely balanced out in terms of size. It's roughly 3,500 elements on it. This little box here is zoomed into here, and this gives you some idea of the sort of complexity of the FPML trade. Let's zoom in a little bit further, and eventually we get some part here is zoomed up to here. What we do see and what we notice is a lot of these elements are optional. They have cardinality, one-to-many cardinality. So if we've got one, let's say a swap leg for something, you could have multiples of those, or you could just have one. So we've obviously got different cardinalities. It's one-to-many, or others are optional. We've got different ways of paying something, so they're optional. The thing is, that's the worst case. So when we go back to this is the worst case that it could be. But when we actually look at the trades themselves, this is probably, I've gone to the extreme, this is the simplest version of a trade. If you can see this, this is a very simple FX swap, a currency swap. So we've got the date, it says it's an FX swap, we've got GBP, the amount, USD, the amount, the date, and the exchange rate. That's pretty much all you need to put in. So we go back 15, 20 years, this was stored in a relational database. When I first started putting these things in, we were using btrieve because we didn't have the oracles and bits and pieces. So we'd bung these into btrieves and using technologies like this on DOS, and we'd store these, and these trading systems would last for years. But over the last 10 years, people have invented new types of trades and new types of derivatives. So these have got more and more complex. When you now start to put these into a relational database, you can imagine the amount of complexity you'll have with these tables. In fact, if we take FPML, it's one of the very first things you can do to demonstrate why the relational database just simply doesn't work, is take FPML, bind it in Java, and then create the Hibernate mapping for that, and you'll end up with something like 1,800 tables. And the joins, they're literally pages and pages in size. In terms of transactions, you'll be lucky if you get transactions per minute out of these sort of things because of literally the complexity. So obviously what we need to do, we still need to store these things. We need to get them into databases. It's even 12 years ago as XML was first coming out. So we started to see these. FPML wasn't around then, but certainly 8 years ago, 2004, etc., when FPML was starting to be used and similar standards, we started to see banks putting these into databases. What they did was to write them in as blobs and clobs. Oracle started to see that this was happening, so Oracle started to come out with its own XML binding. so you had an XML type. You could now extract indices out of the XML and you could put these into the database. So that created some sort of resistance for us. And then you started to get the programmers saying, oh, you know, we got object relational mapping. This is great. We can bung these things in and we can put them into relational databases and we can start to create this with the Java binding. And this ended up with the most horrendous complexity you can possibly imagine. You had pages or megabytes upon megabytes of code that was generated. You had the Java binding generated. You had the ORM generated as well. And what we had was a generated database with a standard and just unbelievable amounts of code behind this, which of course naturally slowed things down further and further. But as I said before, you've got a 6 or 9-figure number, sort of 100 million units of currency spent on these databases, and you're pretty much forced to use them. You've got to go into these. So what we had was effectively putting the XML into the clobs and taking the indices out that you wanted to use. And as we take these out, we can now start to retrieve the elements. So that sort of solved the problem. And we were doing this in banks in about 2004, 2005, by 2006 and 2007, etc. This was fairly commonplace across the banks. So we got all this stuff going in. What we now see is obviously more and more of these trades as derivatives have become more and more used, and we've now got these reporting requirements which are insisting basically that you take all of these things out in an orderly manner, you label them, and you report them to these central reporting or repositories. This is now starting to create a few issues because while we can put them into one of the many, many different databases, we've got to track these things from the front office where they were originally defined, and you've got all the different parts of that. You've got the middle office where it's in multiple stages as well, and finally in the back office as to where it's been paid, because the trade may be paid over numerous parts. So you've got an object which has a rather complex life cycle, which is in multiple parts, which you now have to report. And you now have to search on these things. So this is where we start to see the requirements as we put these effectively into memory. You can still do this on disk, but it's starting to get slower and slower and slower. So what we're finding is the banks are using these relatively frequently used technologies, which have been around, most of these, for quite some time. In the past, this was, should we say, the most innovative banks that were using them. And they were using them because they thought it was a cool technology, or somebody managed to get it signed off, or there was something they wanted to innovate outside of the other banks. What we're now finding, and these are sort of customers of mine, i.e. most of the banks, pretty much every single one of them, well, every single one has to, by law, by the rules, report. And so they now got these massive requirements of huge amounts of data which they have to put into memory, typically, and also persist and report out. So this is now something which, of the last 2 years, I've seen across literally every bank that we've been into and worked, from Japan to Europe to UK to the US. I'm not going to mention any of these specifically in terms of which ones are most popular or anything, but obviously Couchbase, Cassandra, Redis, MongoDB. In terms of if you had 3 stands and you put all those on, everyone tends to gravitate around MongoDB because they probably spend most in marketing. But that doesn't necessarily mean it's the best in terms of persistence. And when it comes to storage, the one that is probably used most is still Oracle. So if you can create an abstraction layer where you're storing key value pairs, and you can keep that abstraction layer, and underneath it put Oracle or MongoDB, for example, what you allow yourself to do is to abstract the implementation that you've chosen to buy. So as an architect, what we tend to promote in this is you don't really want to choose the technology and say, right, we're going to invent a new trading system and it's all going to be based on MongoDB. What you want is to abstract out the persistence layer. And in an ideal case, to be able to choose one of these, or even to be able to move from one to the other, because all of these companies have a habit of changing their licensing arrangements or pricing. Oracle is a case in count. Obviously, the pricing just continues to go up and up. What most banks do is to have two implementations, one Sybase, one's Oracle, and every time one of them comes around to renew their license, they threaten to move to the other one. And so it's just that simple. The same with some of the open source ones. As soon as someone tries to change the licensing, you threaten to move to the open source one because you've got them running in parallel. So I've literally seen all of these. In terms of the in-memory, this is sort of interesting because, again, if you could literally use a Java map. Obviously, you end up with a lot of problems with garbage collection. Then you need to get someone like Kirk Pepperdine in, who's unfortunately in a parallel talk at the moment, to come in and tune it for you. But there's technologies like Azul, which some of the banks were using, which has originally the hardware performance gains. And now they're selling a software version of this, so that it effectively does the garbage collection in a separate thread. Hazelcast is one which I'm going to demonstrate, and also Gemfire, purely because Hazelcast I knew nothing about, and it's something I picked up, downloaded before I jumped on a plane, and managed just to write a little demo in Hazelcast. So I'm not promoting it, it's just because it was something I wanted to learn, and the best way to learn it is obviously to write some code. So the ones we see probably most are the Gemfire, because they were bought by VMware. Gigaspace is still quite a lot around. GridGain. Neo4j is very interesting because it's not a map in terms of for persistence, it's a graph database. Now, if you imagine those green blocks that I showed you, the many-to-many relationships around those as to trades being executed in the front office with one-to-many relationships, with multiple trades referring to the derivatives that are defined in the middle office to multiple different payments in the back office. These all create a perfect use case for something like Neo4j, because it maps the relationships with these. So that's something that would sit on top of these existing products. So basically the flow, if we're putting this, building a large repository in these things, we need to go around and gather all of the trades. Typically that's not a massive problem because most of the databases around there are sort of in existence already, and the vast majority are written in Java. So getting the data out of those is not a huge problem. You then need to understand what you've got, you need to enrich it, need to label it, and then you've got to put this into your central repository. So you've got a bit of integration, a bit of messaging, and possibly a bit of transformation. I'll go through this graphically in a second. We need to extract the information we need to find the trades later. So typically trade dates, amounts, currencies, what we call bit codes, ISINs. These are the entities which the trades are working with. We put these into our in-memory database, which again is the thing I'm going to demonstrate to you, and then we run queries on that, and then those are the exports that go off. So looking at this graphically, it's fairly simple. We go around the 39,000 different databases around the bank. Obviously, they're not all running the sort of stuff we need, but we go around the umpteen dozens or hundreds of databases, collect the information. Typically Java bind it. It doesn't need to be Java bound, but at some point we've got to parse the message to extract the information that's in it. So if you're going to parse it once, you might as well leave it parsed and create it as an object. So we have two choices. We can put the message in its original form, or we can put the message in as a bound Java object. Either way, one of the things that we don't do is to transform the message into something else. If you transform the message into something else, into a canonical format, you are then bound to do that for the entire existence of this application. If the application runs 5 years, you've then got to go back to the messages that you brought in 5 years ago and translate those into the new format if you want to be able to search them. Because remember, these trades, something that was maybe executed in 2006 may last until 2016 or even further. So these things are live and they're sitting in your databases now, and you don't want to have to convert these constantly to a new format. It's a bit like trying to have to force them into a database table. 177 minutes, 175. counter's going. I've got a little minute counter here. It's going really quickly. So as we go through this, we're extracting them out. So what I'm going to demonstrate to you, just in some code, this is, and again, the code is just purely to give you a sort of a feel for how it works. We're going to take some messages out. Rather than use a database, I hate setting databases up, so I'm just going to use a zip file. It's also much easier. In the zip file, I have 50,000 existing trades from an actual bank, which I won't keep on the screen long enough so nobody recognizes where they're from, but they're actual trades. What I'm going to do, I'm going to Java bind them. So I'm going to create a Java object that exactly resembles the original trade. We can do this with any of the message types. I have two choices. As I say, I can either put the message in, I can basically parse the information out, and I can put it in as XML, and that's one typical way. If I'm persisting it over a long term, for example, if I was putting it into an Oracle CLOB, I would typically leave it in its XML format and then come back and Java bind it again. All I need is the schema that refers to or some definition that refers to that message type. In this particular case, because it's going into in-memory, I'm actually going to keep it as a bound Java object, because if I want to retrieve it and do something with it, it's already in that format. If I take it as XML, parse out the information I want, and insert it as a string or a byte array into the in-memory object, if I want to actually get the information out of it a second time, I've got to go back and parse it again, which just is sort of time-consuming. Also, the objects, if we can actually query them on things that we haven't actually created indices on. This is interesting because if you put something into a database and you query something which there's no index, you have to do an entire table scan. This is exactly the same with in-memory. If we put objects into an in-memory database and we query something which is not indexed, we can still get it, but it will go through the entire in-memory database. Interestingly, though, if you've got, let's say, 1 million trades per machine and you've got 1,000 machines, so you've got 1 billion trades, which is not out of the question, it's the sort of realms we're talking about, you can distribute the queries to 1,000 machines. So the 1,000 machines, at worst, only search through 1 million trades. And basically, the trades are already in a format which is that we can actually use practically. So it actually, the queries for even things that are not indexed is extremely quick. And if you've sharded those across 1,000 different machines, and you've sharded it in such a way that you know where the data, most of the data may be, then of course you can send those queries off to a small section of that database. It becomes very fast, or I say database, in memory. So the Java binding's relatively quick. We can use a number of different technologies for this, and again, we don't have to do this. We can actually parse it. I know there's quite a number of banks, certainly with FPML, just leave it in its original format, and they just put it in as byte arrays. There's nothing wrong with that either. They go in as strings. And then writing these into the grid, when I use the term grid, this in-memory database, it's a term we use for about 10 years. So if you like, it's a local cloud. This is typically, they use a map interface. So we can use puts and takes into these things. The interesting part, and this is where it gets a little bit interesting depending on the technology we've used, as we query from this, we get a number of different mechanisms for querying, and this comes down to the actual implementation we're using. So it's a bit like going back to databases before SQL 92 was, or whatever the latest one is. You can tell how long it is since I used the database. 2000, isn't it? SQL 2000? What was that last one? Anyway, but today, if we want to do a SQL query, we have a standardized language. So if we go to a database, it's pretty much standard. When we go to these in-memory versions, we don't have a standard. So they've each implemented different versions of those. And again, this is something which people try to abstract out. Most of them are very similar. So I'm going to demonstrate two versions. I'll do one with Gemfire and I'll do one with Hazelcast. And these are just two different examples, and we can query both of these using different mechanisms. This is where it becomes rather interesting, because you've now need to take care of the indices that you've created. You now need to understand how your query is going to be executed and what indices you may want to create or use. And you'll notice a huge difference in terms of performance if we take the indices out. So now to code. This is the stuff that usually nearly always goes wrong. So I'm going to put it onto screen share. Any questions while I do this at all? You're all grabbing a bit of sleep. No questions at all? All right. Okay, so we've got two versions here. Let's go through the Spring one first. I will make this bigger so that you can see it. Now, what this one's doing, I have a number of these rather nasty looking trades. These are fictitious ones, so I can show you these. This is a thing called Swift. Been around for about 30 odd years or so. Every single bank on the planet that makes payments to another bank outside of its own country has to use this format. So 88,000 different banks. And so it's been around for a long time, and it's around to stay. And they're trying to slowly convert this. This was part of a standard called 775, ISO 775, then it became ISO 15022, and now they're moving this to ISO 20022. It comes in a number of sections. You can see part 1 is up here. That's the header. Part 2 and part 3 is optional. And part 4 is the main body of the message. Inside this, you can see it's effectively tag value pairs. So we've got, let's see if I can find something I recognize. Here we go. 90B is the tag, and the value here is in fact a number of different values. So it's a tag and a bunch of values, if you like. And these are often separated sometimes by characters, sometimes by size and position in there. So what I'm going to do is I'm going to read these in. I'm binding these using Java Binding to something which understands this message. This particular one is, I happen to know in the header here, is a 513 message, and the first letter here is an O, means it's, whoops, if I do that, it will kill it. Hang on. O means it's outbound, so it's outbound from Swift to the bank. So this is a message inbound to the bank, outbound from Swift, if you like. So I'm going to basically read these. Let me show you so there's a big pile of them down here. Each one is slightly different. These are all just generated using random number generators. And this is the interesting part. So I'm running I've just basically run a Spring test. I just want to, this is just an example of what we can do. So again, I'm going to enlarge this so we can follow it through. As I know right, this is the main part of it. So what I'm going to basically do, I'll go through the bits. So I'm going to read in from a textual source factory. I'm going to bind it into a Swift model. I'm then going to read from the input files, which I'll show you these in a second, and I'm going to output it to channel 2. So let's walk through these. So the textual source factory is something which is generated by the Java Binding tool. So this is the textual source factory. It's basically just a parser. The Swift document is, again, the Swift, in this case 2011 MT513 element. Again, this is just the model. This is all generated code behind this. So this is the model of the Swift message. If we're using FPML, it'll be exactly the same. Now I'm going to read. This is my files in here. This is my files in. So I'm reading from the directory that I've just shown you, and I'm going to read all the star.txt files. If I put star, unfortunately it reads dot and dot dot, which fail, as you might imagine. So star.txt, I'm polling it, and 0 weight on that. So it's just typical Spring integration. And then finally out to channel 2. Since Spring bought Gemfire, VMware bought Spring and VMware also bought Gemfire, they've put some nice integration with Spring data. So here's our Gemfire region. It's GFE is the type. I'm creating a Swift ETC, electronic trade confirmation. I've got a cache listener. Now the reason I put a cache listener here is so you can actually see what's going on. I'll show you the code for that in a second. It's just a couple of lines. And this is going to go, here's my channel 2, it's my Swift ETC. And I can actually define, interestingly, the indexes or indices in the Spring config. So as I put these in, I have basically the key is the reference, and the payload, so key value. Now this comes out, what this is doing, this is what we call Sparkle SPQL. It's basically just a language used by most of these technologies, which is just like using the getters. So this would end up being block4.get sequence a .get field 20a, etc. Any Belgians in here? Anyone from Belgium? I know it's going to go out to the Belgians, so I won't be too insulting. But basically, this lovely syntax here was invented by Swift, which happens to be in Belgium. So this nasty block4 sequence a field 20a reference.c.reference is basically from the bound Java code from the lovely syntax that the Belgians gave us. So this is going to go in. So let me show you the listener very, very quickly. So here is the listener. So after create, all I do is print out the key. If I can update, I print out the key and the value. So we'll see the difference. So let me just run this quickly. This is when things always go wrong. Right. So we've got the after create event. This is basic. What it's done now, it's created a Gemfire instance, a local instance. It's read the files and it's bound the files, put them straight into the in-memory database. If I run this a second time, interestingly, what it will do is, so we've got two instances running here. Here's my old one and here's the new one. Because this is a Gemfire region, they will sync across in my network, which is of course my local machine, and they will sync both instances of this. So now we get the values as well as the keys, because what's happening is that the two instances have synced each other. So if I look at the first one, scroll up a bit. Here is the original inserts. This is the update, and then a little bit of logging that we get from the Gemfire database, and now it's actually doing updates. So we get the same message going in the second time, it's actually updating it. And of course now we can go in and query this, which I won't do because I'll do it on the other one, but that's effectively just demonstrating the Swift going into Gemfire without using code. The only code in there is the XML code. I just wanted to show you that. The other one we can query a little bit easier. So let's get rid of that one. Now this one, I'm going to walk you through. I wrote mostly on an aeroplane last week and partly in a bar with Kurt Pepperdine last night, just putting in the multi-threading stuff. So this is the main part of the block. Let's just walk you through this very, very quickly so that you follow it. Right, it's basically a multi-threading version. I'm using a thread pool up here. I'm launching off so here I'm reading in 50,000 messages. These are actual messages. So I'm launching off a zip file reader. I'll show you that in a second. So the zip file reader is basically reading from the zip file, putting them into a queue. I'm using a blocking queue in this case. From the blocking queue, I'm then launching off a number of parsers. Now, the parsing is the slower part of this. So the parsers down here, I launch off a number of these. I start with 8 threads. I'm launching off 6 of these parsers. Reading, obviously, from a zip file and putting them into queue is very quick. Actually, taking the messages out of the queue, parsing them is quite slow. And then finally, I've got an in-memory, inline thing here, which is basically taking them off the queue here, and basically putting them into this Hazelcast map interface. And then once that's done, I've now just put this queries thing here, which is basically just going to take commands from the command line. And what we'll do with these messages is we can actually query the messages and see the messages printing up. So that's basically the part at the bottom is just all it's doing is reading from the command line and basically printing them out. And I'll show you just one of these. We don't need to go through the rest in great amount of detail. So this is basically just, make it slightly larger for you. So it's basically just running through the zip file, taking out the elements, and then just writing them, splitting them, and then writing them into the queues. So it's basically just a mechanism for reading, if you like, off the database. So if we run this, what'll be interesting is we can query this afterwards. So a little bit of debugging here. So the very first item here, this is the reading. These are the items sitting in text format. So these are messages as they've come in text format. So imagine we've read these off the database. These are now sitting in the message queue sides. These are actually parsed. So you'll see this is going up higher and higher, and these are basically the number of messages I now have sitting in my map. This is the Hazelcast map, which again is, if we run multiple instances of this, is distributed. And we're now finished. So I should now be able to query these. So if I say, let me show you what the message looks like, and I'll show you how we can query it. So I've created basically a small message body. This is where I've encapsulated the message. Now the messages can be in multiple formats, and as I said, we're going to be taking information out of the message and enriching the messages in some way that we need to put information about where the message came from, the date that it was there, who booked the message, which database it's in, so as we report it we can come back to it afterwards. So we're taking information out of the message. This body here could be the message in its original format, so we could put a string in there or a byte array, for example. So I've taken out the timestamp, I've taken out the message type because it has a number, I've extracted the currency, and I've extracted the amount out of this. So I can now query one of these, and I've actually created an index on these. And we go down. So if I query, for example, let's say currency equals GBP. So what it's doing, if there's anything more than 2 results, it's basically all I'm doing, rather than obviously printing and scrolling up 1,856 messages, I'm just printing the count in there. So I can narrow this down a little bit further. So I can say currency equals GBP, and amount greater than 1, 2, 3, 4, 5, 6, 7, 8, 100 million. Nothing returned. Let's try something slightly smaller. Okay. If there's a small amount, i.e. less than 3, I basically print out the results. So here it says we've got currency is GBP, pound sterling, and an amount greater than 10 million. So we found our message. This is the ID here. It's timestamp, it's just a nanosecond timestamp. Message ID, the type in this case is a 451. It's just something I've read out of the message. GBP, and then the amount, again, I'm not formatting it correctly, so it's 1.8 times 10 to the 7, so 18 million. And then the actual message itself is here. So if we look down here, we can actually see the part that I've taken out. This is the GBP, and the 18,209,385 and a few pence on that. So basically, that's what we're putting into these banks. Obviously, it's a little bit more complicated than that in real terms, but that's literally what we have created, or what the banks have created, using these technologies. That's what I've got to show you this morning. Any questions at all? You're a very quiet lot. Yes. So the question was, and the query, what kind of syntax that was. To me, it looks very like SQL. If I was perfectly at home with it, I'd be doing select count star from wherever, or select distinct. I would want to do select distinct currencies, for example. I can do that with the Gemfire one, but I can't do that with the Hazelcast one. Again, I'm not trying to compare these and say one is better than the other. It's just my experience with this is 1 week. With the Gemfire, I have a lot more experience with it. There is no standard language for in-memory databases. So one of the things that you've got to, if you're evaluating these products, is not so much the performance. Well, it is obviously the performance, but it's also the languages that you've got behind it. The interesting thing is this query, I'm typing it, so it's obviously parsed and evaluated. I could do the same query in code as well. So I can actually say map.select, and then I can put in quotes, and I can basically build this up part by part. So I think most of the in-memory vendors create something that people are happy with, which is close to SQL. So that's pretty much what we've got. We can do ands, ors, greater than, less than, in, between, these sorts of syntax. But not all of the syntax, such as order by, max, aggregation, things like that. Any other questions? I know I'm holding you back from lunch, but it's not there yet.
So you've got all your data into in memory, and you're talking about millions and millions of rows. Obviously, you wouldn't want to load them all the time. Is there some sort of persistence that's actually going on under the hood there?
Yeah, typically, so the question's about we wouldn't want to load them all the time, and what is the persistence behind these? It's quite similar to same techniques you'd have with a classic database in terms of archival and what tables you'd have available. So if we're reporting, we'd be reporting typically live or active trades, whereas ones that are inactive, we'd be putting into a storage mechanism. One of the advantages of this, as you've seen, we can retrieve the trade, and all I'm doing here is a toString. The toString returns it into its natural form. So part of what I was looking at earlier was, for example, the backends. Now I could layer this on top of Oracle. I could have used coherence, which is what Oracle would prefer me to use, obviously. So I could use coherence to do my queries, and I can do exactly the same. I have a coherence example here. And then behind that, or behind this, I would archive stuff off to a CLOB or an XML blob in Oracle. Or if I'm lucky enough to have one of the other NoSQL databases, and I'd effectively put it into some other format and persist it on that. So there's live, and there's, should we say, archival as well. And we do the same in retail. If we're not using transaction data, we can use cloud. So typically we'd have archival on S3, we'd put Elastic Block would be sort of more up-to-date stuff, and we'd have a large instance of a machine with a lot of memory to run the daily stuff. Any more questions?
So you can only query on the fields that you pull out into the domain model, so that you can only query, say, the timestamp and message type of currency. Is that true?
Yes. Okay, so the question is can we only query on this? So the answer is sort of not entirely clear. It's not yes, no. I created a message type, and what it's done is expose those to allow me to query them. So you saw the message that I created. I have UID, amount, and currency. So yes, I can query on those easily. However, if I was to go down into, let's say this field 16S, for example, I can also query this as block. I could go block 4, so I could do select block 4 dot field 16S dot whatever that is. And the problem is that different message types will have different structures. So one of the reasons why I took out, for example, the amount is because you'll see here there are multiple different amounts. And in these multiple different amounts, which one is the one that I'm actually looking for? So I had to write some code when I insert it in to look for the one that has set for settlement, and that's the currency and the amount that I'm using. So if I was trying to do a query on this would be like selecting something from a database where we've got a table we need to do a join on, which would actually slow things down quite a bit. So I would then need to do select where field 19A, and you see we've got multiple 19As in here. And then you'd have to say where 19A equals settlement and then select the other one. So let me show you the query for that. This is where I actually extract the information out of that 19A, just to show you that. So here's the 19A. If you can hopefully see that, make it slightly bigger. I'm looking for the set for settlement, and I'm trying to get this currency and amount field out of it. If I do it in XPath, this is the syntax. So it's basically MT541, block 4, sequence E3, because they have multiple parts of these, and then field 19A amount qualifier equals set in brackets, and then I basically get the currency and amount. I could do that, and I could execute that if my in-memory database executed XPath, as Gigaspaces can, for example. So that query I could run directly on it. What I'm actually doing is doing that in code, as you can see here. Oops. Where I'm basically iterating through the multiple versions of those, looking for the one with the word set in it, and then setting it to the currency and amount, as you see there. Then I'm enriching the message, currency, and amount to make the queries easier. So as you put multiple trades in, generally what you're going to do is header enrichment. So you extract the information that you'll probably want to use. But if we wanted to go in and do a very specific query, we can still query the message itself. But it would be very difficult to build indices on this because of the multiple levels of dependencies and the multiple different types and the multiple levels in there. As you can see, to build an index on XPath like this would be extremely complicated. I doubt even whether I'm pretty sure Oracle wouldn't do it either. So even if you're putting that into an Oracle database using XML, you would still have to manually extract the information and create it on top of that. But you can query the information in the database without extracting it. It just gets more complicated. Any more questions? Yeah.
You said that banks generally like to not bet on one horse and have two implementations. Would they also do that for those in-memory solutions? Where they say, well, this is nice, we will do Hazelcast and we'll do Gigaspaces.
So questions about, as I mentioned, banks like to have multiple implementations, and would they do this within memory? Yes, they would, and that's very typically what happens. So you tend to look for an implementation. Somebody might actually say, why do we need to buy one of these? We can do this in our own implementation using a Java map, for example. So there'll always be one person fighting for let's do it for free, and there'll be someone else using some other open source implementation from JBoss, for example, and someone else that's met a couple of vendors and wants to do the vendor implementation. So these will go quite a long way in parallel. Where it gets really hard is because there's no standard. And when you get down to the queries, you're going to have to ultimately implement those queries in some sort of language, and you've got to go as far as you can to create multiple versions of it, but at some point you're going to have to pretty much commit. Do you mean from one implementation we do multiple queries and join them afterwards, or?
Well, or if you have this whole system with 15,000 databases which you want to get into in-memory databases, that you reuse that, read those, or what is the best practice for that? Any idea?
What's the best practice for getting these out? I don't think there is a best practice, to be honest. It's stuff which banks have been doing for many years, but it's really, we're starting to see this being done. I mean, every bank does it. I think it's also fair to say every bank has probably every implementation of this. Every bank is divided into what we call lines of business, and in one you'll find Tangasol, another one you'll find Gigaspaces, another one you'll find Gemfire. And internally they'll all be fighting for which is the best implementation to use. So you'll have multiple versions of this in pretty much every bank. It's very rare that enough projects can get together to influence somebody higher up in the bank to actually make a purchase for a global purchase. because again, you're competing with the IBMs and the Oracles who've got these 9-figure deals. And then someone says, well, we've just spent 100 million on Oracle and we've got Tangasol across the board. Why are you trying to get Gemfire or Gigaspaces in here? Just makes it difficult. If we have no other questions, I'd like to thank you very much.